After quietly exploring the cosmos for over 40 years, NASA's Voyager 2 has finally spoken from interstellar space, and what it revealed has left scientists stunned. This wasn't just another routine signal. Voyager didn't simply drift beyond our solar system. It uncovered something long overlooked, a sharp, mysterious boundary at the edge of the sun's reach, marked by sudden bursts of radiation, shifts in plasma, and questions that shake our understanding of space itself. So, what exactly did Voyager 2 discover, and why is NASA so shaken? Launched in 1977 with a life expectancy of just 5 years, 10 at most, Voyager 2 has defied time and distance, surviving nearly half a century in one of the harshest environments imaginable. Battling intense radiation, freezing voids, and the endless emptiness between planets, it has never stopped whispering back to Earth. Now, following in the path of its twin, Voyager 1, this trailblazing spacecraft has officially crossed into interstellar space, making them the first human-made objects to reach beyond the Sun's sphere of influence and into the galactic unknown. But this milestone is more than symbolic. Voyager 2's instruments recorded abrupt, measurable changes in plasma density, temperature, and radiation, evidence of a dramatic shift from one region to another. The transition wasn't gradual, it happened almost instantly, as if the spacecraft had stepped through an invisible doorway from the solar system's protective bubble into raw galactic space. This shocked scientists, who had long expected a slow fading of the sun's influence. Instead, Voyager found a distinct sharp edge, like crossing from one room to another, suggesting our solar system may be more neatly defined than we thought. Right beyond this invisible wall, Voyager encountered hotter particle energies, higher radiation, and much more turbulent conditions, the kind of environment that would challenge any unshielded spacecraft. In confirming the boundary's existence, Voyager 2 also revealed just how vital the Sun's magnetic bubble, the heliosphere, truly is. Once believed to fade gently into the interstellar medium, we now know it ends in a sudden drop-off, acting like a shield that protects our planetary home from the full force of galactic radiation. Even more surprising, Voyager 2 detected an almost perfect alignment between the Sun's magnetic field and that of the interstellar space beyond. This discovery clashed with decades of theories and forced a major re-evaluation of how our solar system interacts with the galaxy around it. To make things more complex, the heliosphere may not even be stable, expanding and contracting with solar cycles, changing the very shape and location of this cosmic threshold over time. One of the most remarkable takeaways from Voyager 2's crossing was how precise and fast the changes occurred. Plasma density didn't just rise, it spiked. Radiation didn't drift in, it surged. Rather than slowly fading, the Sun's influence dropped off, as if Voyager had stepped through a membrane into another world, one far more energetic, unpredictable, and uncharted. Voyager 2 discovers a cosmic barrier that changes everything. When space scientists analyzed data from Voyager 2, they were stunned, not because the numbers slowly shifted, but because the changes came all at once. Instead of a gradual fade, the spacecraft recorded sudden jumps as if it had crossed a cosmic threshold. The technical name for this invisible border is the heliopause, the outer edge of the Sun's influence. What shocked many experts was just how precise and well-defined that boundary turned out to be. One moment, Voyager 2 was still inside the protective zone of our solar system. The next, it had entered a vastly different region dominated by the galaxy at large. Beyond that invisible edge, the levels of galactic cosmic rays surged by nearly 70%. That dramatic spike confirmed something long suspected. The heliosphere, the magnetic bubble created by the Sun, acts as a kind of shield, filtering out high-energy cosmic radiation that would otherwise bombard our planetary neighborhood. Outside this bubble, Voyager 2 was fully exposed, traveling through an environment filled with fast-moving, high-energy particles. And it didn't stop there. As scientists looked more closely at the shape of this mysterious barrier, they realized it's not a perfect sphere. Far from it. Voyager 2 revealed that the heliosphere's edges are distorted, uneven, and possibly even pulsing. Over the Sun's 11-year activity cycle, its magnetic field can expand or shrink, which may cause the boundary to shift. That's likely why Voyager 1 crossed the heliopause at about 119 astronomical units from the Sun, while Voyager 2 reached it farther out at around 121 astronomical units. It wasn't random, it was dynamic. This raised a bigger question. Is the heliosphere part of a larger moving cosmic interaction zone? The idea that this boundary might be alive, reacting to solar changes, shifting with galactic conditions, began to take hold. Every new signal Voyager 2 sends adds to our understanding of how much this frontier moves and how unpredictable it really is. Sudden spikes in temperature, waves of particle density, and surprising changes in magnetic direction all point to a boundary that is anything but static. And once Voyager 2 passed through it, it entered a new environment, interstellar space, and started encountering what scientists now call interstellar weather. This includes fluctuations in cosmic ray intensity and subtle energy shifts that could be linked to far-off galactic events like supernova explosions or fierce stellar winds from distant stars. While Voyager 2 doesn't have the instruments to directly observe these events the way telescopes do, it can feel their effects. Changes in energy levels, magnetic twists, and particle flows hint at what's unfolding across the galaxy. Why the heliosphere matters. The Sun is constantly blowing out charged particles, a stream called the solar wind. Along with the Sun's magnetic field, this wind forms a protective bubble around our solar system known as the heliosphere. Think of it as a cosmic cocoon. It deflects or weakens many of the high-energy cosmic rays flying in from the rest of the galaxy. These rays aren't just exotic, they're dangerous. Too much of this radiation can damage spacecraft systems or even harm biological tissue, which is why the heliosphere is more than a scientific curiosity. It has real importance for space travel and for life on Earth. For decades, researchers debated where exactly the solar wind gives way to the interstellar medium. Early theories suggested a soft transition, but Voyager 2's data told a different story. It found a sharper boundary, a narrow zone where the conditions changed quickly and significantly. That discovery reshaped how we view the Sun's reach, proving that it can hold off cosmic radiation more effectively than once thought. As Voyager 2 approached this frontier, scientists closely watched changes in plasma density, particle speeds, and magnetic field orientation. Over and over again, the data showed a clear point where the Sun's influence stopped and the galaxy's forces took over. Inside that line, it's all about the Sun. Beyond it, the wider galaxy rules, redefining the edge of our solar system. New data from Voyager 2 has reshaped how we think about leaving the solar system. It's no longer just a poetic phrase, it has structure, depth, and surprising complexity. One of the biggest takeaways? The boundary between our solar neighborhood and interstellar space isn't fixed or evenly shaped. Some scientists now believe the heliosphere, the Sun's protective magnetic bubble, may stretch out behind the Sun like a tail, much like a comet, while appearing more compressed at the front as the Sun moves through the galaxy. Both Voyager 1 and Voyager 2 support this idea. The bubble isn't a perfect sphere, but just how asymmetrical it is remains an open question. What these missions reveal is that space weather doesn't stop at Earth's orbit. Events like solar flares, coronal mass ejections, and the Sun's magnetic cycles can cause the heliosphere's outer boundary, called the heliopause, to shift. What's more, forces from beyond our solar system, such as interstellar storms or bursts of radiation, may also press in from the other side, warping or squeezing that boundary. One major confirmation came from the dramatic increase in cosmic rays detected outside the heliosphere. The data clearly shows that the heliosphere acts like a radiation shield. It's not a physical wall, but an organized flow of magnetic fields and solar particles that create a distinct difference between inside and outside. Voyager 2's instruments recorded how starkly these two regions contrast. a vital insight for anyone planning long-term missions into deep space, where future spacecraft or astronauts will need to endure harsher, high-radiation environments once they've exited the Sun's protective envelope. A surprising magnetic alignment. One of the most unexpected findings from Voyager 2's journey was the nearly perfect alignment between the Sun's magnetic field and the magnetic field of interstellar space. Scientists originally thought there would be a mismatch, a kind of magnetic clash or turbulence where the two fields met, but instead the fields lined up more smoothly than predicted. This raised fascinating possibilities. Maybe the Sun's outflow has subtly reshaped the magnetic field in the local interstellar medium. Or perhaps we just happen to be traveling through a region of the galaxy that already aligns well with our Sun's magnetic field. Either way, this smooth alignment is prompting new questions about how our solar system fits into the galaxy's broader magnetic architecture. It also matters for cosmic ray transport. High-energy particles like cosmic rays are guided by magnetic fields. If the fields are misaligned, these rays might take longer, more winding paths to reach us. But if the fields are aligned, particles could stream in more quickly, which is exactly what Voyager 2 observed. Cosmic ray levels spiked almost immediately after it crossed the heliopause. Some experts have questioned whether this alignment is constant or whether it might shift over cosmic timescales. Another factor is the Sun's 11-year magnetic cycle, where it flips its magnetic poles and changes solar wind intensity. These shifts can cause the heliosphere to expand or contract, and may even influence how and when spacecraft experience magnetic alignment. Voyager 2 happened to cross during a particular phase of this cycle, a detail that may help explain the clean alignment it observed, though it still goes against many long-standing astrophysical models. 2 Voyagers, 2 stories. Though both Voyager 1 and Voyager 2 crossed into interstellar space, they didn't have identical experiences. Voyager 1 made the leap first, around 119 astronomical units from the Sun. Voyager 2 followed a bit later, crossing at about 121 astronomical units. But the differences didn't stop there. Each craft measured slightly different temperature shifts and radiation patterns. The data from Voyager 2 wasn't just a repeat of Voyager 1's, it was a unique glimpse into how the heliosphere might behave differently in various directions. These differences support the idea that the solar system's outer boundary isn't a uniform shell. It's more like a responsive living edge that shifts, stretches and pulses based on solar activity and galactic forces. Thanks to these 2 legendary spacecraft, scientists are beginning to map a truly 3-dimensional picture of where the Sun's influence ends and the galaxy takes over. Sharper eyes on the edge of space. One key difference between the 2 Voyager missions lies in their instruments. By the time Voyager 1 reached the edge of the solar system, its plasma sensor was no longer fully operational, meaning it couldn't directly measure some of the most critical changes. Voyager 2, however, still had a working plasma detector when it crossed into interstellar space. That gave scientists a more direct look at how plasma density changed, not gradually, but in a sudden, almost jarring leap. This sharper data opened new questions. Could the boundary between the Sun's influence and the galaxy beyond be flexible? The evidence began to point that way. Rather than a fixed line, the heliosphere's edge appears to be constantly reshaping. Part of the reason may be the Sun's 11-year activity cycle. Periods of stronger solar wind push the boundary outward, while quieter phases let the galactic forces push back in. But that's not all. There may also be shifting conditions in the interstellar medium, from dense gas clouds to changes in magnetic fields, influencing the shape of the boundary. Even the direction each spacecraft took could play a role, since the Sun itself is moving through the galaxy, potentially leaving a tail or wake behind it. Another clue came from tracking cosmic ray intensity. Both Voyager spacecraft recorded an increase in radiation once they exited the heliosphere, but the timing and scale of that increase varied slightly. These differences, recorded at distances less than 2 astronomical units apart, confirmed that the boundary isn't a smooth shell. It acts more like a flexible membrane, bulging outward in some areas and curving inward in others. And these shifts weren't just theoretical. Each time a spacecraft crossed through specific zones, the data reflected real changes. In short, these missions turned into a live experiment for studying how the solar wind meets the galaxy, offering insights no telescope could capture from afar. A shifting, breathing frontier. Voyager 2's data painted a picture of a dynamic edge where solar winds and interstellar forces constantly interact. A frontier that moves and morphs, not a frozen shell. Earlier illustrations of the heliosphere showed a smooth, static boundary, but reality seems far more alive. Think of the boundary like a cell membrane, responsive, flexible, and influenced by its surroundings. The Sun's magnetic cycle breathes energy into this space. When the Sun is active, it pumps stronger solar wind into the void, pushing the edge outward. When solar activity dies down, the galactic medium pushes back in, creeping closer. This tug of war changes the flow of cosmic rays. During active solar phases, more magnetic pressure means those high-energy particles are kept farther out. But during quieter times, they sneak closer and even seep in. This pulsing can cause localized breaches, where interstellar particles mix with solar ones, a sort of cosmic osmosis. Some researchers have compared the heliosphere to a living, breathing system, expanding and contracting with the Sun's rhythms. Over the course of each 11-year solar cycle, the Sun flips its magnetic poles, shoots off plasma, and erupts with flares. All of these events ripple outward, eventually reaching the edge. Voyager 2 has been instrumental in tracking how these events coincide with, or slightly lag behind, changes in charged particles and magnetic field strength at the heliopause. But the Sun isn't the only player. As our solar system speeds through the Milky Way, it passes through patches of space with wildly different properties. Some areas are thick with dust or gas, others carry leftover magnetic forces from ancient supernovae. When the heliosphere drifts into or out of these regions, it adjusts, and Voyager 2 records those shifts. Although we can't predict every cosmic condition we pass through, the Voyager missions continue to offer clues, showing us that the boundary between solar and galactic space is not just real, it's alive. A mysterious, layered boundary. One of the most surprising revelations from Voyager 2 was how quickly some of the changes occurred. If the edge of the heliosphere faded gradually, scientists expected to see data ramp up slowly. Instead, they saw abrupt, sudden transitions, like stepping across a threshold. This sparked new theories that the boundary isn't a single smooth line, but may contain layered zones, thin, ring-like segments stacked one after another. As Voyager 2 crossed each of these layers, it recorded brief but noticeable changes in temperature and cosmic ray levels. These step-like jumps supported the growing idea that space isn't uniform, but is made up of magnetic microenvironments, small, distinct regions shaped by invisible forces. Thanks to Voyager 2's real-time data, scientists could finally piece together a more detailed map of space's hidden architecture. The 2019 blackout and strange signals Voyager 2's incredible journey hasn't been without drama. In 2019, the spacecraft suddenly went silent. Its instruments shut down unexpectedly, and for several tense hours, there was no signal. Then, just as mysteriously, Voyager 2 came back online, all by itself. NASA engineers labeled it a glitch, likely tied to the craft's aging systems or a software hiccup. But some wondered if the deep interstellar environment had played a role. Beyond that, a handful of curious anomalies have popped up. Odd spikes in electromagnetic readings that don't match known events like gamma-ray bursts or distant supernovas. Some of these are probably just instrument noise or random interference, but a few can't be easily explained. Could Voyager 2 be sensing unknown features beyond the heliosphere? It's possible, though hard to confirm. Because Voyager 2 is so far from Earth, communication is slow. Instructions sent from NASA's Jet Propulsion Lab take hours to reach it. If something goes wrong, the probe has to rely on its own backup systems, just as it did during the blackout. That ability to self-correct may have saved the mission. Still, some scientists, and many space enthusiasts, point to a deeper mystery. A few data patterns don't line up with any known source. Could they hint at unfamiliar cosmic forces? Or is the culprit simply the aging sensors on board a decades-old machine? The answer is still out there. Is the solar system's edge being watched? Here's where the theories turn speculative. Some have floated the idea that the boundary of the heliosphere might be more than just a barrier. It might be something like a monitored checkpoint. This isn't a mainstream scientific belief, but the Voyager data does feed into the curiosity. The transition from solar to interstellar space wasn't gradual. It was precise, sudden, almost too sharp to ignore. Radiation, plasma density, magnetic field direction all shifted at once, as if crossing a line drawn in space. Skeptics suggest that this kind of precision doesn't necessarily mean anything is monitoring the boundary. Instead, it might be a natural outcome of how solar magnetic fields interact with the galaxies. Just like rivers can meet with sharply defined borders, the sun's outflow might merge with interstellar conditions in a way that creates sudden transitions. And then there's the golden record, the message to the cosmos that both Voyager spacecraft carry. It includes instructions on how to find Earth. Some critics have called this bold or even reckless. What if the edge of our solar system isn't just shaped by physics, but is somehow structured or aware in ways we don't yet understand? Still, these are questions for science fiction, not formal science. NASA hasn't found any proof of observers or intelligent design at the edge of the solar system. But the clean boundary, the fast transitions, and the unexplained data spikes have certainly inspired more than a few cosmic what-ifs. NASA's take: no gatekeepers, just physics. NASA officially attributes the sharp edge of the solar system to natural physics, not to anything like Guardians or cosmic watchers. The data Voyager 2 sent back, including sudden spikes in galactic cosmic rays and abrupt shifts in the magnetic field, is viewed as normal for crossing a well-defined boundary in space. Whether that boundary is just naturally distinct or part of something more complex is still up for debate. One key mystery is how consistent that edge is across different directions and whether it changes in real time. Some scientists suggest the boundary acts more like a responsive layer than a static border, shifting based on the tug-of-war between solar forces and the galaxy beyond. Another idea? That Voyager 2 may have crossed a concentrated region of radiation, not a warning zone, but simply a more energized slice of space shaped by magnetic fields. Even the 2019 glitch Voyager 2 experienced might have been random, yet these quieter physics-based explanations still leave room for awe. Whatever the cause, this mysterious outer region continues to intrigue both scientists and the more imaginative minds that follow their discoveries. Flexible boundaries and uneven edges. One of the more unexpected findings was that Voyager 1 and Voyager 2 didn't cross into interstellar space at the same distance or under the same conditions. Each probe recorded a different pattern of cosmic rays, plasma shifts, and magnetic changes. This told researchers the boundary isn't fixed like a perfect shell. Instead, it seems to stretch and shrink depending on direction and cosmic influences. Many now think of the heliosphere, the sun's protective bubble, as being shaped more like a comet or teardrop than a sphere. Its size and contour change throughout the sun's 11-year activity cycle. During high activity, solar wind pushes the edge farther out. During quieter times, the bubble contracts. Interstellar conditions like gas clouds or magnetic fields can also push and pull on it from the outside. Voyager 2's plasma readings helped confirm that this boundary isn't rigid. High-pressure areas appear to resist cosmic rays better, while low-pressure spots let more of them slip in. These movements aren't just theories. They've shown up repeatedly in the data, proving that the heliosphere adapts constantly to both solar activity and galactic weather. In short, this isn't a static wall, it's a dynamic interface shaped by everything inside and outside our solar system. The differences in data between the two Voyagers helped NASA build a more three-dimensional view of this border, which is why the two probes were sent in different directions to begin with. Even individual cosmic events, like distant solar eruptions, can send shock waves that ripple through the solar system for years. When those waves hit the edge, they might shift the boundary or stir up temporary changes. And if a probe is out there at just the right moment, it might catch those disturbances or sense the aftershocks moving through interstellar space. Rethinking the edge of our cosmic neighborhood. Voyager 2's final confirmation of crossing into interstellar space didn't just mark a milestone, it shook up our view of what leaving the solar system really means. For years, space was imagined as quiet, empty, and formless. Now we know our solar system is surrounded by a vast magnetic and plasma-based structure, a kind of invisible bubble that protects us from the full chaos of galactic radiation. It's not a wall you can touch, but a boundary with measurable properties. Once you step past it, everything changes. The radiation spikes, the plasma behaves differently, and the sun's influence fades. Voyager 2's discoveries suggest we live in a structured, ever-shifting cosmic zone, far more alive and complex than past models imagined. The boundary isn't just a marker of where our solar system ends. It's a clue that space is layered, active, and filled with surprises waiting to be uncovered. We're starting to see that space isn't just endless emptiness, it's layered. There's the solar bubble that surrounds us, a boundary where it ends, and beyond that lies the wider galaxy, filled with stronger radiation and very different magnetic fields. This discovery shifts how we see our place in the cosmos. We haven't simply been floating through space, we've been protected. The sun's heliosphere acts like a giant shield, filtering out much of the harsh galactic radiation. We only truly understood how vital that protection was when Voyager 2 crossed the edge and sent back the data. The spacecraft revealed a sudden dramatic shift as it exited the heliosphere, like stepping out of a calm room into a storm. Temperature spikes, stronger cosmic rays, and a magnetic field that changed almost instantly pointed to a much sharper boundary than scientists had expected. Inside, the sun's magnetic influence dominates. Outside, it's the galaxy's turn. And this barrier isn't fixed. Thanks to Voyager 2, we now know the boundary moves, stretching, shrinking, and reacting to solar flares and interstellar disturbances. It's a dynamic front line between our solar system and the rest of the galaxy. But there's more than just science here. There's wonder and even a bit of caution. Voyager 2 carries the golden record, a message from Earth sent into the unknown. It's a bold gesture of contact, but some wonder if it's also a gamble. Wherever that record ends up, perhaps drifting for millions of years, it reminds us that we've announced ourselves to the cosmos. Even after Voyager 2's systems shut down, likely by 2025, the craft will remain out there in the dark, holding that tiny disk. What we once thought of as a gentle fade into deep space is now seen as a layered transition zone, a frontier that clearly separates the sun's influence from the galaxy beyond. By stepping across it, Voyager 2 proved that space changes in real, measurable ways. It revealed that cosmic rays are far more intense beyond the solar shield, and it helped redefine how we understand space travel, interstellar weather, and the edges of planetary systems. Thanks for being here. If you enjoyed this journey through the unknown, don't forget to check out the next video on your screen for more insights from the edge of space.